today's lecture is actually the most important in the whole series, because previous lectures were a kind of preparation to what you will hear today. And this part really gives a solid theory. Then during the remaining lectures, we will talk about the vertical structure of accretion disk, a lot of other things, but then a lot of hand waving will be involved. Assumptions, additional assumptions, complications. So you will see why the standard theory, which we will discuss today, sometimes works and sometimes does not work. But the theory is solid, and it's important to understand why it works when it works. Why it works, well, we will discuss today. When it works, we will discuss more during the next lecture. I mean, the underlying assumptions. So today we will assume just Newtonian physics. We will forget basically about general relativity, pseudo-Newtonian things, whatever. On the other hand, we will rely heavily on this idea of marginally stable orbit, or ISCO. This we will use, and this will be a very important part of the lecture. So in the case of Newtonian mechanics, you all know that this angular momentum is a square root of gm times r. And we will now concentrate on the part of the disk which is far from the actual source of the material. When we were talking about Roche overlap and flow through L inner Lagrange point, we had certain angular momentum and then circularization orbit, and then the material had to somehow settle. This is very complicated region. So now we will assume that we will discuss just the part of the flow which is well below this troubled region, where the material slowly drifts. The radial velocity is much, much smaller than the Keplerian velocity of the rotation. So we will assume that we have almost circular orbits, and the dynamical role of the radial velocity is negligible. And we will discuss this issue in detail. So first we can discuss a bit in more detail the accretion efficiency, although in the case of disk and issues related to black hole accretion and ISCO, we did this discussion before. But I also wanted to call your attention to the case of a star, because that is different. And this is why in most of the remaining lectures, we will not talk about accretion onto stars, because that's again a problem. Why it happens? Why? We introduced this efficiency of accretion in the case of radial inflow. That was done during the first lecture. And then we got the efficiency, which is equal half of the short side radius over the radius of the star, of the central star. Now, if we consider that this Keplerian orbits, those Keplerian orbits approach the star, then the binding energy at the stellar surface in Newtonian approximation or close to the stellar surface would be like this. So then the total efficiency is actually factor 2 lower. Why is that? Because still this material contains a lot of Keplerian or a lot of motion, kinematic velocity, right? Rotational velocity. So this is why at the same radius, vertical radial inflow is more efficient, because then the material comes to stop here, right, at the stellar surface, because it just falls down and stops here, while here it approaches along circular orbits, and half of the energy is still retained in the form of kinetic energy. Okay, but if the star does not rotate, what actually should happen? Because we cannot just be in a situation that we have here strong rotation, very large velocity, and here the stellar surface is actually at rest. There is a strong friction between the stellar surface and the Keplerian disk. And it's really strong because in most cases, the rotation is really negligible. For the case of the sun, if I did not make a mistake, then the velocity at the equator is of order of 2 kilometers per second, linear velocity, right? But if you calculate the Keplerian velocity there, and if you imagine that some accretion disk would approach the sun, then this Keplerian velocity would be 400 kilometers per second, a huge difference. So in most cases, you can consider that the star is actually at rest. And then you have a huge friction between the outer disk, where you have still this Keplerian rotation, this is a cross-section disk, and the radius. So finally, this material has to come at rest. This angular momentum has to be given to the star or what, but we need some kind of transition zone between those two things. So finally, actually, we will reach the efficiency, which was the same as in the radial inflow. But that means that we have that amount of, if I can go back. Yes. So this will be the efficiency of an accretion disk, a quarter of this ratio, while the total efficiency is that. So we need to dissipate the amount of energy, which is also equal to that, and only in a very narrow zone. That's really a dramatic event, because you have the same amount of energy dissipated in large accretion disk. And then another, so this is 50%, and then 50% is dissipated here, very close to the disk surface. And you don't know the angular momentum distribution, anything. And calculating that is very complicated. So you can imagine that what happens to the angular velocity is that first you follow this disk, circular orbits, and then you have Keplerian angular momentum. And then you have to go to zero, because then you have to come to rest with the star surface, or you can have very, very little of this rotation. So you have a kind of maximum here. This is actually also important, and maybe I should mention that later. At at that point where you have the derivative of angular momentum, of angular velocity 0, viscous forces also do not work. Because, you know, if you have a rigid rotation, you have no viscosity, right? So in a sense, you can describe the accretion disk here in that part using a standard approach, because this you will have a 0 torque boundary condition. On the other hand, you have to describe that part, and you have to dissipate here another 50% of the energy. And then it's not clear whether this emission is optically thin, optically thick, what's the profile, what's the distance. We have no way to estimate this. This is really a topic which is still under discussion. Modeling is very difficult. And in the case of full GR, the situation is actually even worse. If you consider main sequence star, then you don't have to trouble about full GR, and this statement that half of the energy is dissipated here would be okay. But if you consider neutron star, for example, then GR effects are important. And in that case, if you calculate this more carefully, it seems that you should dissipate here 2 times more energy than here. So the situation is even worse. So you have one spectral component of non-shape, and then something which is 2 times more important, and you have no idea what to do with that. Of course, this material has to spread over the star. It's not obvious it will spread all over the whole star, or it will form an equatorial belt, or what. And yeah. So this is why studying spectra in the case of X-ray binaries containing neutron stars is much, much more difficult than black holes. Black holes are simple, and we will concentrate on black holes. Okay. So now first we will do not correct estimation of the flux which is dissipated in the accretion disk as a function of radius. But this exercise is convenient because that intuitively and simply show how this works, that we don't need any information about the viscous forces. We will assume that orbits are just Keplerian orbits, circular Keplerian orbits, and that's enough. So you must say that there is some viscosity, otherwise nothing would happen. But otherwise, if you assume that you have certain stationary accretion rate, certain drift from one orbit to the other, you can describe the whole disk without knowing anything whatever about viscosity. And that's the important thing in this classical simple theory. In this way, we will get one of the coefficient in the final flux not correct. But otherwise, the method of computing is very simple, because you have those Keplerian orbits. So you assume that its angular momentum is given as it is given, and then you know what is the total energy at a given orbit. So now you can calculate the difference between the orbit r plus delta r and orbit r. The difference in energy. And this is the expression, and we will assume that delta r is small. So this is the correct expression, but if delta r is small, you can combine those two terms, and you will get a term half gm over r squared, still times this size. So this is the energy, the excess energy, we have to get rid of when coming from this orbit to this orbit, and this is measured per unit mass, per gram, for example. So then if we introduce accretion rate in grams per second, then we have an energy which should be dissipated in grams per second. We just multiply this expression by that, and now we change the sign because we are interested in the energy which gets out. And this energy has to be radiated by the disk in this zone between that radius and that radius. So then the surface is equal to PR times delta R. And we have additional factor 2 because we here assume that the emission is optically thick. So then the disk will have two surfaces. Upper surface and lower surface. So if you calculate only the flux per surface, you have to introduce factor 2 here. So now you divide energy by the surface, and you have a final prescription for the flux dissipated here, 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 as a function of radius. No viscosity, nothing, right? So it's just proportional to the central mass, to accretion rate, and it goes down like RQ. So this is not exact formula. We will determine the exact formula during the next part of the lecture. This will involve a lot of mathematics, but the result will be sort of similar. So this is really important. You don't have many assumptions here, but of course you use the angular momentum distribution, you use the energy equation, and you use the continuity equation. So here I stress again that viscosity is not needed. It does not enter the formula. On the other hand, if you have no viscosity, then you would have accretion rate equals 0. So in a sense, it is encoded there, but if you assume it's stationary, you don't mind how it works. So of course, in reality, you can have examples when you have beautiful disk. Those are the Saturn rings. Excuse me, still remnants of this throat problem. But in that case, we have no accretion. And collisions are very infrequent, so accretion is negligible, and this is not an accretion test. So now we will start proper derivation of the formula, and it will differ in this coefficient, which was in front. On the other hand, it requires quite a lot of work and mathematics, and in some moments we will do it a bit more general, in the sense that the assumption of stationarity will be introduced a little later than it could be, but we will need those equations during one of the next lectures when we will talk about the time evolution of accretion disks. So now there will be really a heavy mathematics. But restating again equations, we have those circular orbits, this ISCO or marginally stable orbit. So this is a top view of the accretion disk. But we have to look also at the vertical cross-section of an accretion disk. Here I used a kind of triangular approximation, but we will later assume that what is important is that the disk thickness is much smaller than the radial distance at this moment. in detail, we will discuss those underlying assumptions during the next lecture. And we will assume that this disk is optically thick. So as I said, we will have to use continuity equation, angular momentum, and energy equation. So we start with the continuity equation. This is this general form, which was already on the previous lecture. But now we will change coordinates into cylindric coordinates, because in the case of accretion disks, usually most computations are done in cylindric coordinates, because this is more convenient. So the continuity equation in cylindric coordinates looks like this. And then, of course, there is a lot of things which change in the vertical direction in the disk. Here, the disk is hotter, here is cooler, the density profile is complex, the temperature profile is complex, but we want to forget about it. So we introduce a quantity which is named surface density. And there is always a problem of two, because some people, when introduce surface density, they integrate from below up. Sorry. Wrong direction. Some people introduce this integration from below the equatorial plane to the top. So from minus infinity to infinity. Most people define it integrating from 0 to infinity. It's a factor 2 difference. I hope I did not confuse anything during the lecture. Anyway, we will assume that we have axial symmetry, and we have, of course, also the symmetry in the equatorial plane. So what is below looks exactly like what is above. So how we really use this idea of surface density? We have to integrate this equation with respect to the coordinate z. So here we have this integration. Now we integrate from minus infinity, but this will look like 2 times this surface density. Then we have to integrate this part and this part. This part will be simple. So as I said, this will be replaced by the surface density, or 2 times the surface density in that case. This is simple to integrate, because if you integrate a derivative, then you have the value of the function at the limits, upper boundary and lower boundary. So if the velocity, vertical velocity is 0 at the disk surface, if you have no wind, then this is just 0. And we have only to fight with this expression, which is not very nice. It should be small r. I thought I corrected that, but somehow, I don't know. Sorry for that small r. So again, we have to introduce the accretion rate, but this time we do it a bit more generally. Previously, we introduced stationary accretion rate. But now it's in general, this accretion rate can be a function of time and radius, but nevertheless, this is 2 pi r and times the amount of material which is flowing, which is density times radial velocity, and integrated over z. In spherical coordinates, it was easier. You did not have to integrate. You had just 4 pi r squared. So now with those new quantities, you can have a general expression for the continuity equation, and as I said, we will use it later, where you have that the time derivative of the surface density equals the space derivative of the accretion rate. So in the case of stationary situation when time derivative has to be 0, of course you integrate this equation and you have the accretion rate is constant. That's really obvious. But now we will have to work with the equation of angular momentum transport, which is a bit more complex. So this was the kind of preliminary exercise. So now we start with equations of motion in 3D. It looked like that, Navier-Stokes equations, where we have viscous force and gravity. And now we studied everything in cylindrical coordinates. So we use cylindrical coordinates. And as I told you, we will be interested only in one component related to angular momentum. And that is the phi component. So, okay, this percent is, again, some small mistake in typing those stupid formula is quite complicated. And when I use OpenOffice software, then to get the Greek letter, I have to write percent and the name of the letter. But because I made here a mistake by typing 2i, then the stupid software did not understand what I had in mind, and I did not notice that. This is what happened. So it should be dv phi over d phi. Fortunately, this will simplify quite a lot because we assume that we have axial symmetry. So any derivative with respect to phi will be automatically 0, like this derivative, partial derivative. So it's not a problem. And in this case, d phi is just the Keplerian velocity. So it does not depend on phi. We just know that it does not depend. So it's not even a stationarity assumption. It's just an assumption of Keplerian motion. So that is also 0. So that remains because the derivative of the Keplerian velocity over r is not 0. And we have to keep the radial velocity. So that remains. And this remains. And this again is 0 because Keplerian velocity does not depend on z. So this derivative is also 0. So all what remains is here. It looks really badly, but in that case, it's really convenient to introduce not velocity, but angular velocity density. And in that case, you can write this equation in such way. So you have just the derivative rate of the Keplerian angular momentum with respect to radius. And this is now obvious why I said we will care about the angular momentum equation, right? This is the angular momentum equation. And then this radial dependence of angular momentum equation depends on viscous forces. So for the moment here, we have to use certain idea of viscous forces. Only later we will have to get rid of this. Because I told you the final expression will not depend on that. But here we do one assumption. To write this term, to go from this general term to this term, we just assume the velocities in the 5 directions are the highest. So then the friction works really between Keplerian orbits and transfer the angular momentum in radial direction. And this is why only R phi component of the stress tensor remains. And we don't have to say anything about its form, but for the moment it's here. So again, we want to use continuity equation. We want to use accretion rate. So we do similar approach as we did before. But we multiply equation first by 2p r squared to get rid of this. Oops. Which is back. No, that is back. Okay, yes, we are here now. So we multiply by this. Somehow if I keep this pointer a bit longer, then it changes side. Not this way. This way. This way. We're here. I think it's a problem if I press it centrally, then it works as a pointer, and if I press it off side, it really changes slides, and that's a subtle issue. Anyway, we integrate again this equation, both sides in z direction. So that looks like the accretion rate which we had before. That still looks hopeless, but we can exchange integration with respect to z and calculating derivative with respect to r. And we cannot do much with this expression, but we introduce new quantity, which is the integrated stress tensor. If we introduce such a quantity, then we have a very nice simplified expression, and in that form we can easily calculate the final expression. We integrate. That is possible only if we finally assume that the disk is stationary. Once again. It goes again in this. Because if accretion rate is a function of radius, we cannot integrate this equation. On the other hand, if we assume that it's stationary case, then it's a constant, and then integration is simple. And because we integrate, we have to add certain integration constants. And now those constants will be very important. So here I put two constants, one L in and then theta in this integrated stress, because I first could not decide where to set the boundary conditions. But now we will use this knowledge from full GR and from existence of ISCO, innermost stable orbit. There, I told you, viscous stresses should be 0. So then, again, it's going in the wrong direction. Okay. So then it's convenient to formulate this inner boundary condition exactly at ISCO, where you know that stress is 0. So this theta in will be just 0. You can forget it. And then you know, of course, what is the expression for the angular momentum at the marginally stable orbit. So now you are set. Apart from the nasty situation, we still have this theta here hanging, right? We have no idea what it is, apart from the definition viscous forces. But we still didn't use the energy equation, right? And previously we used energy equation. So now we have to work with energy conservation, and that is even more complicated. So I didn't write this full equation in cylindrical coordinates, but you can always find Eulerian equations in cylindrical coordinates. And here we will assume immediately that we have a stationary case, and we will neglect radial gradients or vertical gradients which are connected with the flow of the energy with the matter. We'll concentrate on that part, and here you have radial derivatives of the radiation flux and vertical derivatives of the radiation flux. And because the disk is thin, then vertical derivatives are much larger than radial derivatives, because everything changes in the distance, which is really small. We'll discuss this in more detail during the next lecture. So finally, this thing will reduce to the derivative of the radiation flux with respect to the radius. Here we have also conduction flux for general purpose. We will neglect it. And then we have this term related to viscous forces. And then again, if we assume that only this R phi component of viscous stress is important, only this friction in circular rotation, we know from physics that this term is equal to the same TR phi, which we were using before, times radius times the derivative of the Keplerian angular momentum. So you see that stresses here are 0 if this is 0, but normally this is not 0. So now we end up with such an equation, which looks much simpler. So here we neglected also this part, which is so-called advection term. We will talk slightly about it at the end of the lectures. And this form now is ready to do what we did before. So we integrate this over this coordinate C. This is simple because then it gives us just the flux at the disk surface, and that's it. Or actually two fluxes, because one is on the top, one is at the bottom. And here we can return to this value theta integrated viscous stress, which we introduced before. So we have something like that. So we have now two equations. This one, which we got from the angular momentum, which contains theta, and this thing, which also contains theta. We have no idea what theta is, but now we can combine those two equations, right? Putting the theta from this equation into that equation, or whatever. And you can calculate, in that case, the flux emitted from the disk surface. And this is the final expression. This is how it's customarily expressed. Omega is the Keplerian angular velocity. So here you have derivative, but you know how to calculate derivative of something which changes like r to minus 3, 1.5. How to say 3 seconds in English? 3 halves. Okay, whatever, 1.5. So this is finally the expression for the radiation flux which we wanted to have. And this is really exact expression in the case of Newtonian approximation using the idea of ISCO. And again, it does not contain viscosity forces. On the other hand, it differs from the previous expression because, again, because you have here factor 3, and here you have this value of this angular momentum, Keplerian angular momentum at ISCO orbit. So you can guess immediately that it will depend on the approximation. If you use pseudo-Newtonian, whatever, we will talk about it at the end of the lecture, it will be different.
Sorry, I didn't understand one thing. So even without the knowledge of what the stress tensor is, how can we get this formula? I mean, where is it? It's vanishing.
How to go back to this. This is what happens. You have two expressions. Here you have theta. Here you have theta. You put this into that, or that into this.
Yeah, so I mean, still we have one information lacking, isn't it? We do not know the exact.
But we don't need it.
We don't need it.
Yes. You still do not see that, right?
No, I can see that it is in between. It's
hidden
in, right?
Yeah. Yeah, but this is a factor which you know, right? This is what you know, the value of the Keplerian angular momentum at ISCO.
I see. Okay.
And this is this theta. On the other hand, this theta is equal if you calculate from this other expression f dot. And we have to divide, there is -1, and we have to calculate here the omega over dr. But omega, as I said, is r to minus, so the omega over dr is actually minus this omega over r, right? So you have to work a bit, and then you have to remember that this is exactly correct. So then finally you get rid of omega, and you have this expression, and that's it. So as before, if you use a combination of the angular momentum conservation and the energy conservation, you don't need viscosity. On the other hand, if you want an answer to the question, how thick is the accretion disk, then you have to answer this question. So this works only for the flux. And it's important to really see that.
I have a question. Like,
yes,
this radiation flux that we got, it depends on m dot and also r. Now,
yes.
if we compare this flux to the local radiation, I mean, to the luminosity Eddington limited, like for certain value of m dot and at some position at r, it can exceed.
Oh, well, but you have always to check and do.
So what happened then next? Exceed.
In that case, if you approach Eddington luminosity, you cannot neglect the terms which we neglected. For example, in the equation of energy, because we neglected, for example, this advection term. And this is, for example, characteristic for slim disks. You have to include slim disks. You also have to include then departure from the Keplerian motion, because then your radial gradients of the pressure become non-negligible. So you have to calculate actually then the angular momentum distribution, because radial gradients of the pressure will be important. So we will talk a bit about some things during the next lecture, but for those departures, we will need explicitly the knowledge of viscosity. But for that formula, we don't. So this is the beauty of this formula, but it cannot apply always everywhere. Okay. So this part here is quite important, because you see that this flux is then equal 0 at ISCO. And this is what we actually expected, because there is no viscosity acting on ISCO. So this is how the distribution looks like if we plot symbolically this flux as a function of radius. It falls down as r to -3, but it reaches the maximum somewhere and then goes down at ISCO. And this maximum is actually quite close to ISCO, so a lot of energy is dissipated in this region. If I did not make a mistake, then this maximum is located at 27 divided by 4 Schwarzschild radius. And roughly half of energy is dissipated inside 10 Schwarzschild radius. So a lot of energy which you see from quasars, for example, is really dissipated close to the black hole. So now it's possible also to determine the effective temperature in the disk if we assume that the disk locally radiates as a black body. Because this is then simple, we have flux. So then we assume that flux is equal sigma times effective temperature to the power 4. So determining the effective temperature as a function of radius is really simple exercise. And the plot looks more or less similar. The temperature goes down here as minus 0.75. And the maximum of the temperature, again, if I did it correctly, is located quite close to ISCO. It's at 49 divided by 12. So it can be calculated analytically. You have to calculate the derivative of this stupid formula and put it equals 0. So it's as simple as that. But now it's interesting indeed to put into this thing which is reading things which are expressed as functions of Eddington ratio and solar mass. So I did that for this maximum value of the temperature at this point. And then I got the value 6 times 10 to 6 kelvins. Here is this ISCO position. For a star, you have to modify that. So this is why I kept this expression here. So you see, there is a strong dependence both on Eddington ratio and the black hole mass. But if we assume that we are actually close to Eddington ratio, then for the mass equal 1 solar mass, you have temperatures like 10 to 6. That means your radiation is in X-rays. This is where you expect the emission of accretion disks in binary systems, in X-ray band. Because if it is 1 or 10, it does not matter. On the other hand, if this is 10 to 8, then 10 to 8 to power 0.25 is 100. So we are going 100, factor 100 lower. So instead of 10 to 6, we will get 10 to 4. 10 to 4 is UV. So in the case of AGNs, quasars, the disk emission will be visible in far UV. And we can compare this formula to what we had during the first lecture or second lecture for the spherical approximation, when we just did hand waving. Well, almost order of magnitude the same, right? So those initial approximations were also not that bad, right? But this is much more accurate, and it's a bit, the actual value is lower than in the case of the spherical accretion when the matter is stopped at the surface of the star. Okay, now more advanced and difficult thing, which is still based on what we derived. Because if we have flux at each radius of the disk, we are ready to calculate the spectrum of the disk or the wavelength dependence of the emitted radiation. For that purpose, we have to expand our knowledge from just the total flux to wavelength dependent flux. On the other hand, we have to integrate over the disk surface. So first we will start from the single black body. So single black body emission looks like that, and in many cases this is plotted as a function of wavelengths. But it can be also plotted as a function of frequency. Only you have to be quite careful because power law dependencies are different if you use wavelength and if you use frequency. But you can always change one version to the other using this expression, that lambda Planck function as a function of lambda is equal nu times Planck function as a function of nu. I'm usually using this other version. So they look like inversion of each other, right? Almost, but the slope is different. So if you are close to the maximum this temperature or maximum temperature, then of course your emission goes down. And at longer wavelengths or shorter frequencies, you can determine the power law dependence. Because this is the expression for the Planck function. This is something which we don't need at this moment. Oh, sorry. So if we consider frequencies which are much smaller than the temperature, then this term can be expanded as 1 plus this minus 1, so this remains. And then you have nu cube here divided by nu, and you get nu square. So then this part asymptotically behaves as nu square. So it's quite steep power law, and then it's this exponential cutoff related to the maximum temperature. So in principle, you should do this exercise numerically. So it's basically simple. But then you also have to include that if you really look at the system at certain viewing angle, you see the disk not face on. We previously calculated just the total flux emitted at each angle. So it was integrated flux. What we see should depend on cosine of the viewing angle E. And of course, if the disk is edge on, then the flux is 0. Because we assume it's infinitely thin. So first, you need to know the effective temperature as a function of radius. Then knowing the temperature at that radius, you can calculate the emissivity at each frequency and radius from the Planck function. And now you have to integrate that over the radius and multiply by cosine I, this viewing angle. And then you have a distance to the source, d, you have to divide by d squared. And this is then the observed flux from the source. So in general, this has to be done numerically, but we can get asymptotic expression. It's not quite simple, but you see that most of the problem is this denominator, right? It's a kind of troublemaker. So then you introduce new parameter, which is equal T. But first, you also have to supplement here this radial dependence. So all looks like this. Then to simplify somewhat, T0 is introduced, which is stays in front, simplifies a bit thing. So this is a new coordinate, and that allows to write e to t minus 1 here. On the other hand, now the integration, instead of being done over R, has to be done over this new parameter t. So you have to calculate this, the radius as a function of this parameter, and it's this kind of a power law. And you have R dr. So you have complex here power law containing t, then it's t dt divided by e to t minus 1, but that looks kind of dimensionless, right? On the other hand, you produce a lot of things in front, and they will go in front of the integral because they do not depend on the radius. And the important things which go into the front is first frequency. So frequency was to power cube because it was here, nu to power 3, right? And then from this change, you get nu to power 4/3 minus, again back. And then you have also the r, and it gives you another term like this. So finally you have 3 minus 8 divided by 3. So finally you have mu to the power 1/3 as in front of the integral. Then you have to work with this in the same way, converting T0 to accretion rate and the black hole mass. And then radius to black hole mass. You have to work out all those components, and then you will notice that you will have mass times accretion rate to the power 2/3 in front of the integral. And then you are still left with this stupid integral, but this is kind of dimensionless. So if your frequency is far from the energy corresponding to the peak of the temperature, you can say that you perform this integral from 0 to infinity instead of caring about exact values. And then it is a numerically something like 2.5 or whatever. It does not matter.
I have a question. So if we are on the same plane of the black hole, on same plane of the accretion disk, an observer, so according to that formula, we won't be able to receive any radiation?
Yeah, because this is what you would see, right?
So how do people then take the spectrum of the Sagittarius H star?
Well, because you first of all, you are never edge on. Second, Sagittarius A star does not contain a optically thick geometrically thin disk. So, as I said, the model does not apply to everything. And if you have optically thin emission, then emission is almost spherically symmetric, independent of geometry or dynamics. But if you have a thin disk, yes. And here it's an assumption that disk is actually infinitely thin, which is never properly correct, because if you have a side view, then you would see the outer edge of the disk, right? So then geometry would be completely different, but we cannot use this. So for example, if you have a disk like that, halved, and then your observer is like this. In binary system, in ecliptic system, this happens. Then you would see this part. But we assume that this is almost 0. So then this approximation, again, is not correct. So, if you want to have a simple formula, it's like with tools, right? If the tool is simple, it's not really suitable for everything. So then we can get rid of this thing, calculating numerically. And finally we get, I didn't write this proportionality coefficient because every time I try to do it, I get it wrong. So sorry for that. But anyway, you have a prescription for the integrated flux from an accretion disk, proportional, as I said, to cosine of the viewing angle, depending on the distance. But frequency dependence is as a power law, 1/3. And here you have the normalization, which depends on black hole mass and accretion rate to the power 2/3. So then this accretion, this shape differs from a single black body. Single black body would be this part, right? And it describes more or less well the high frequency part of the spectrum. On the other hand, here you have a contribution from the outer parts of the disk. So instead of the slope 2, you have slope 1/3 only. It's a large difference. And then if you do observations here at long wavelengths, you are not affected by this part. And then you can use this power law approximation, and it's frequently done like this in spectral analysis when you do not expect that you should see the curvature of the spectrum. And here everything is known. I stress again this proportionality coefficient is also known, only I did not put it here properly. So now we will shortly say when we can compare this model actually to the data. So it's not working always, but in many cases it does. So this is really great. So for example, here is a pretty old paper from, about dwarf novae. This is Z. Camelopandalis, I guess, right? This is a system. Dwarf nova is a system belonging to a general group of cataclysmic variables. So it consists of a white dwarf and the main sequence star, and the accretion flow proceeds through the inner Lagrange point. The disk there is not stable. This is the bad news. So here you see the light curve of the system. This is time. It's a bit too low. And this is the luminosity. So from time to time you see outbursts in this system, but of course those outbursts take several days. So you can observe the source during several days of the outburst. And this is what those people did. They observed the source during the outburst. And then they were able to determine the temperature profile of the disk, because this is an eclipsing source. So if you have a disk, you do not resolve the disk, but if the other star shields just more and more of a disk, more and more, you do not always see whole disk. So you can divide pieces of the disk into those which are visible at this moment and those not visible. And then if you model the whole eclipse, you can actually recover under certain assumptions the temperature profile of the disk directly from this kind of eclipse analysis. And as you see, that kind of technique was used really many years ago, and it was quite successful. So what you see here is the radius, and here is the temperature. So lines are models for different accretion rates. And those are observational points. And you see, they really align along the model. It's a very good description. The classical Keplerian disk is a very good description of dwarf novae during the eruption. The problem is that between eruption it's not. But you know, life is not simple. By the way, this light curve is still a good example how astronomers, amateurs, can contribute to science continuously, and they do. So this AFSO, you know how to spell it more elegantly in English. This is a database where amateurs from all the world put their observations. Cataclysmic variables are their favorites, but they observe also blazars, whatever. You always can go to this database and you can have a really amazing, long, pretty dense light curve with errors, of course, because the data comes from different observers. But there are no professional light curves of this type because large telescope is too expensive to observe this source continuously. Amateurs have time. So, you know, the paper is really from 2013. So this is not that this kind of observations were important, let's say 60 years ago. No, they are important still now. Professional telescopes cannot cover all sky all time. So in the case of dwarf novae, it's occasionally working. In the case of low mass X-ray binaries, this also look not that bad. There are occasions when this works. So in the case of low mass X-ray binary, I remind you, we have a neutron star or a black hole and the main sequence star filling its Roche lobe. In the case of neutron star, no, it's not working because I told you there is this difficult boundary layer which gives 200% of the luminosity, and then modeling is very difficult. But in the case of black hole in soft states, the model of a standard accretion disk applies. So here is a paper from Ayakubota and Makishima, 2004. So this is the original paper, X-ray spectrum. So this is the whole spectrum. But this is the disk component. And here they add, oops, again. So they had to add additional component to model this part of the spectrum above 10 keV. But you see, this is more than 2 orders of magnitude, right? So this additional component is not really important below 10 keV. Below 10 keV during the soft state, the model works sometimes very well. In this soft state usually appears when the Eddington ratio is above few percent. On the other hand, those soft states are not also always identical. Here is a collection of spectral shapes. This is from Don and Gierliński. You see that sometimes the disk is in low hard state, and then it does not look like anything. On the other hand, there is a variety of soft states. This is standard high state with strongish tail, ultra soft state. That looks very nice, right? An accretion disk, 2, almost 3 orders of magnitude, some tail below. That's really a minor correction. Very high state, it's more problematic because it's almost like soft state, but then this tail is kind of important. And we will talk about this in the context of Comptonization during the next lectures. But you see, from time to time, it is really, really a very nice disk. In the case of AGNs, again, in some cases, it works really very nice. This is the spectrum which we published a paper on this spectrum in 2011. This is only the optical UV spectrum. We don't have X-rays, but we have a point here. So I would put quite a lot of money into statement that this source is really, really X-ray weak. And if it has any X-ray emission, it would be, I don't know, few orders below. So it's not important. And all this is really very nicely modeled by a standard equation. Usually in this part, it's more problematic, but if you have only this part, then the standard model works frequently quite well. This is just a small fragment of optical UV spectra from Capelupo. I cut it really part because they had several more examples and they were more or less identical. But you see, this is here the data. Oops, again. Here is the data. A lot of emission lines. So of course the standard disk cannot model emission lines. There are also things like that, but this is pseudo-continuum. This is Fe2 emission. So it's almost like line, or it's like hundreds of thousands of emission lines. But the model is very nice. This is again standard accretion disk model. On the other hand, if you look at some other objects, and this is a larger range of composite spectra from Richards et al., you see that, well, this should be the accretion disk component. And again, this should be the accretion disk component, close to 15 in those units. But you see, X-rays are not that faint, and of course there is a lot of infrared emission. So this component do not always dominate, but still in those spectra it more or less dominates. So it contains 70% of the luminosity. So standard disk works for most quasars to some extent. Of course, M87, I didn't use Sagittarius A star, but it would be the same story. For a classical accretion disk, this is a catastrophe. So this is the broadband spectrum of M87. You see two bumps, but this is jet emission. This is synchrotron, and this is synchrotron self-Compton. We will talk a bit later about it. Standard accretion disk should be somewhere here at 10 to 15. I do not see such a component. Nobody does. So this is a source which has very low Eddington ratio, something like 10 to minus 5. On radio maps, what you see is basically a jet emission. This is really large scale jet, and the closer you see, the more collimated jet part you see. And finally, you have this event horizon telescope image. And now I think more and more people believe that this is also a jet in projection. Alternative is that it is a hot flow, but not a classical standard cold accretion disk. So in low Eddington ratio sources, you cannot use the standard accretion disk model.
Excuse me.
Yes.
It cannot be the case like that disk emission has been suppressed by the jet emission. Like,
no, there is no cold disk there. No evidences. But for this emission, it's difficult to say because you have a mixture of inflowing plasma and outflowing plasma. And predictions from the model really depend on the assumptions about non-thermal particles. If you put more non-thermal particles into the jet, which is reasonable, then you enhance emissivity of the jet, and thermal synchrotron emission is not efficient. Synchrotron emission on non-thermal particles is extremely efficient. So everything depends where you will put non-thermal particles of a power law distribution. No temperature, nothing. So it has no connection with standard accretion disk. Maybe there would be something at larger distances, but from SED we do not see that. So I mentioned that briefly, that we derive everything using Newtonian approximation and the idea of ISCO. That actually, if you change the approximation, you change this factor, which is in the prescription for the flux. So it is important, finally, for the final computation of the accretion disk spectrum, which approximation you use. The problem is that numerically these things become more complicated. If you Newtonian case was simple, pseudo-Newtonian case is more complicated, but it's actually pretty similar. Schwarzschild case is already dreadful to calculate, but still analytical form. In the case of Kerr metric, which describes rotating black hole, this contains this additional spin parameter A. This is not done analytically. There is no compact expression like this. You have to calculate it numerically. But nevertheless, the final expression for the accretion disk emission has the same form. Similar scaling, 3G black hole mass accretion rate divided by 8 pi r cubed, and no dependence on the viscous forces, but complex dependence on radius and spin, and always this is 0 at the marginally stable orbit, and this factor goes to 1 as we go to infinity. But this dependence on the spin is pretty strong. So this, on one hand, really allows to calculate the value of the black hole spin. And the method is relatively simple if you have an idea about the black hole mass. You need an independent measurement of the black hole mass. You need an independent measurement of the viewing angle, and you need an independent measurement on the distance to the source. Then if you know the black hole mass, then from the power law part, then from the power law part, you can calculate the accretion rate. Because this power law part is not depending on the spin. And then if you see the peak of the luminosity, then this depends, then you already have an accretion rate, and then you can determine the spin easily. On the other hand, if you don't have an independent knowledge, for example, of the viewing angle, then the problem becomes more complicated, because this is an example of few spectra for different viewing angles. So here the normalization changes. But if you don't know the viewing angle, then you can model that changing accretion rate. So if you change here accretion rate to adjust to the data, then you lose the absolute information about the black hole spin, because then accretion rate and spin are coupled. In principle, in full GR, there are relativistic corrections which are slightly depending on the viewing angle, but they are so subtle that you would need accuracy of a few percent at that tail. It's not doable because usually, as I showed you before, here you usually have additional components like comptonization, whatever. You don't see that. And even in the optimum situation, sometimes you have problems. This is the plot for LMC X3, where the viewing angle is known, black hole mass is known, distance is known. But you see what happens. This is the paper by Odele Straub. This is her PhD thesis a couple of years ago, but the problem is formally still not solved. She calculated, because for galactic sources, they are getting brighter, less bright, whatever. So she took all the data, and then the same source, was at different Eddington ratios. And she determined the spin for each observation separately. So at low Eddington ratio, she was about 0.6, but then the stupid spin went down. So it looks like when source is brighter, the spin is lower. That is not possible because I told you about the Salpeter timescale. To change the mass or to change the spin, you need 10 to 8 years and not half a day. So this should not happen. This should not happen. It's just something wrong with the model. Of course, you can. They tried to use sling disks, but they did not solve the problem. So even advection term did not solve the problem. You can solve this problem assuming outflow, for example. Because for the disk prescription, we assumed we have no losses from the disk surface. If you have mass loss, you don't have the conservation of mass, and then you can modify the flux prescription in kind of arbitrary way. So problems are even in the simplest case, but no. I didn't promise to solve all the problems using the standard accretion disk. So this will be the end of the material for today. And this is the homework. So calculate in Newtonian approximation the radius which divides the disk into an inner and outer parts which radiate equal amount of energy. I told you it should be at about 10 Schwarzschild radii if I remember correctly. But I would like you to calculate that.